Well, thank you so much, everyone. I really appreciate it. And I wish I could be there in person, but I'm really looking forward to hopefully bringing us home on the topic of AI. You've heard, no doubt, some sort of great conversations around how to leverage AI platforms, how to consume AI services, how to use fully managed services. And so this focus is really going to be on how do you leverage the power and capabilities of Kubernetes to do model training, model serving, and to build heterogeneous applications. So we'll focus on sort of some high level here, and then we'll get down into the weeds. And we're going to end this with a demo. And this is a demo that is brand new, literally like minted today. So I am very excited to be sharing it with the audience today. And so we'll get into the technical stuff here as quickly as we can. So I'm excited for that. Maybe I'll set a little context. Hopefully this has been a theme you've actually heard throughout the course of the day. We're seeing from our customer base that generative AI is becoming increasingly critical as an integration into products and digital services. That's from every organization up to the largest ones that are building models and providing them as services. That's a very small minority of customers, but those customers have specialized demands. Through to customers that are adapting those models, taking a model, fine-tuning it, deploying it for their own service. Or customers that are sort of consuming out of the box or open models that are openly available, which are becoming increasingly sophisticated and capable. So really what we help customers to do within Kubernetes and within GKE is to provide a lower level of control for customers who are doing all of these things. We're really building AI into the core of their products and really want to leverage state-of-the-art accelerators as well as the scale and efficiency that Kubernetes provides to build AI platforms. Now, the challenges we've seen, I think you've heard this pretty consistently today, model sizes continue to grow. They're really pushing the limits of infrastructure and scalability and obtainability, increasing price performance pressure, meaning that in order for a lot of these AI products to be economically viable, they need to absolutely be as price performant as possible. Squeezing every dollar out of those accelerators is a critical action for customers that are deploying at this level of scale. And then we also recognize there's a lot of complexity, especially if you think about heterogeneous workloads, like the application that Lisa was talking about. You've got the front end, you've got some decisioning, some chaining, and then you've got the back end that's actually doing the serving. We think about all of these AI workloads as being naturally heterogeneous. So how do we leverage those more effectively? And one of the ways in which we do that is to leverage sort of the broad scope of Google Cloud's capabilities within AI that we call the AI hypercomputer. And really specifically, we try to leverage as much open software as possible. This is true across the open ecosystem for machine learning tools and frameworks, like LangChain, like so many others, Ray, and the list goes on, but also in the core orchestration, and that is Kubernetes. And we really like to say that GKE, Google Kubernetes Engine, is the operating system of Google Cloud's AI hypercomputer, because it really helps to scale and orchestrate the workload across all of the storage, compute, and networking to deliver that best price performance. Now, in order to do that, there's quite a bit of components that are under the hood, and so we'll go through them sort of piece by piece, and we'll go a little bit deeper as we go through the course of the afternoon here. So at the foundation, of course, this is leveraging purpose-built infrastructure for AI. You've heard about this throughout the day. So we're leveraging the same CPUs and GPUs and TPUs. You can orchestrate them just as you would any other node, and you can get the efficiency of delivering this across thousands of nodes, connecting to storage, using best-in-class networking across nodes, across GPUs, across regions, etc. And if you sort of go up the stack a little bit more, this is where the Kubernetes management that is really optimized for AI comes into play. This is where we can leverage that decade's worth of experience in building complex enterprise-grade applications and delivering that kind of capability for AI workloads for both inference and training. And this is everything from all the optimizations we can do to accelerate workloads, and we'll talk about that, through to how do you ensure that you are optimizing your cost and your performance while also ensuring obtainability of those resources, and then managing large fleets of clusters and nodes and resources across across large teams as well. And then we want to do this in a way that we're leveraging open frameworks for AI and ML, everything from Spark to Kubeflow to Ray to Q. We really want to provide the best tools and frameworks and resources for customers so they can provide sort of an interactive development experience via notebooks. They can expose things like jobs APIs. They can serve endpoints for optimized inference. They can build heterogeneous apps all in a single platform. So when we talk about GKE for AI, we really focus on scalability, helping customers to scale for both inference and for training use cases, doing that with a managed Kubernetes experience, increasing, really optimizing price performance through a concept that we call good put, which we'll talk about here momentarily, and doing that in a way that it can be ultimately multi-tenant or highest efficiency, and then ultimately helping customers with that level of agility that's necessary. We know this space is moving incredibly fast. And so we want to help customers if we can shave a week off of deployment time. That's going to give customers a competitive edge in the current day and age that we are when it comes to Gen AI applications and services. Now, you've also heard a little bit about scale. I think Yishan talked a bit about how we look at scale. And again, this is really for the largest customers who are deploying very large sets of clusters that are specifically designed for training, say training foundation models as an example. But this scale, we really like to work with customers that are growing quickly. We want to ensure that they are comfortable with the level of scale that is possible and capable within GKE. So everything from being able to deploy very, very large clusters of 15,000 chips in TPUs, or excuse me, 50,000 chips of TPUs to 15,000 nodes per cluster. So we can scale up very large and we can scale up quite fast. But we can also scale across the most comprehensive portfolio of AI accelerators in the industry. That is everything from GPUs you've no doubt heard about today, all the way through our TPUs. I'm not going to spend a ton of time talking about these accelerators, but just know that all these accelerators are designed to be able to be available and sort of fit the right workload for the use case. Everything from the sort of lower cost inference cases all the way through to the very large scale training with GB200s and V200s that we're going to be shipping later on this year and early into next year. All right, so generally when we talk to customers about building AI platforms and building them on Kubernetes, we generally talk about these three use cases. And hopefully these are going to be relatively self-explanatory, but I'm going to break each one of these down, talk about exactly what they mean conceptually, and then talk about some specific customer scenarios, customers that were very successful with each one of these use cases. And then we'll get down into the nitty-gritty, talk about some of my sort of favorite capabilities that we're shipping in the product to help deliver against these use cases. So the first one, building an AI training platform. Now, this might be pretty obvious, but if you think about scale and how scale increases, this idea of productively using your resources goes from a nice to have to an existential problem. You've probably seen the numbers of how much organizations are spending on GPUs and how critical GPU resources are for a lot of organizations. So for large scale deployments, this idea of ML productivity is absolutely critical. And so when we're working with customers, we introduce this concept of what we call good put. Now, good put is essentially a way of measuring ML productivity. And it breaks into three different categories. And if you sort of sum up these three categories, that gives you a number. It gives you a percentage. 100% is sort of the best number, sort of the impossible number to get to, but we want to get customers as close to 100% productive as possible. And if you were to just use a baseline example, by the way, the Gemini team responsible for, or the DeepMind team, excuse me, responsible for training Gemini, they published about a 97% good put for their resources. And they use Borg, which is the predecessor to Kubernetes, and they use containers and a lot of the same sort of technology we're talking about here to train the largest models in the industry, that is Gemini. So we sort of break these down into three categories. First is scheduling good put, and that's really the fraction of time that all resources are available. The next is runtime good put. It's the fraction of time that all required resources are doing what's called making forward progress. Meaning if you're training a model, how much forward progress are you making in order to actually achieve your outcome of a trained model? And then the last is program good put. Essentially the fraction of peak available compute that's being utilized by the program. There are so many flops that are available within these resources. There's quite a few of them for the largest ones. So how are you ensuring that you are maximizing the utilization of those resources on which the program is deployed? And for each one of these, the platform, the platform teams are ultimately responsible. Really, the GKE team as a product organization is helping customers to optimize every fraction point we possibly can. So with scheduling good put as an example, we can help with things like optimizing node provisioning and scheduling using queuing and what we call dynamic workload scheduling, which we'll talk about here momentarily, or all the way down to pod optimization, where we can do things like image preloading and introduce high throughput pod scheduling. So we can ensure that as pods need to be scheduled up, let's say there's an outage or something happens with the training run, we need to ensure that as many pods are available as quickly as possible with high throughput scheduling. On the runtime side, we want to help with things like data availability, preloading, and caching, as well as things like auto checkpointing for disruption management. And ultimately, these GPUs and TPUs, we want to ensure that they are as efficiently utilizing their time as possible. So as much as we can preload the data, pre-cache the data, that's obviously going to help with that overall performance. And then checkpointing is a critical aspect of performance. A checkpoint is basically the saving the state of the training run at certain increments. And if a failure were to happen, and GPUs and TPUs, they do fail from time to time, especially in these large distributed clusters of thousands of nodes. So we want to introduce things like auto checkpointing to ensure that we have a checkpoint that's available and we can go back to it to minimize disruption wherever possible. And then last, on the program side, this is where we're investing heavily in things like ML frameworks and benchmarking tools that work across both GPUs and across TPUs. So you'll see lots of work that's happening in the TPU ecosystem. We know lots is naturally happening within the GPU ecosystem. And we want to be sure that we're providing best-in-class frameworks and capabilities so customers can measure their good put, improve their good put, and then ultimately maximize utilization of those resources.
Hey, Brandon, how does
a great example
like
of a customer who's done just that is Character AI. Now, Character AI, they essentially craft personalized AI. So they've got a great user experience that's available through an app, highly popular. And it allows the members to essentially...
How does something like good put, how is that factored into GKE or a customer? Is the customer actually seeing a good put metric for their work, or is it something that you're managing to say, I want to hit a good put of 75%, and I will manage GKE as a managed service to make sure that happens? I'm just trying to understand. I understand the components of good put, but I'm not sure how you're using it.
Yeah, so that is our North Star. It's a great question. Ultimately, what we want to do is expose this metric to customers in an easily consumable way. Right now, we have tools that make it easy for customers to track this across sort of distributed clusters. But yes, that is essentially the idea. We want to expose this metric, just like we've exposed CPU utilization and other things that are quite common in the industry. This is sort of a new metric, which is becoming increasingly critical for large-scale training. And so we're sort of doing a lot of education really in the industry to help folks understand exactly how to measure this. And we have tools and capabilities that make it possible for you to expose these kinds of metrics. But yes, that is the idea, right? In an ideal world, where we're going as a platform is to expose this directly to users so users can incrementally improve that number over multiple training runs. Thanks for that question. And keep the questions coming, by the way. All right, so we talked a little bit about Character AI. They're using both TPUs and GPUs, and they're doing some pretty amazing stuff when it comes to large-scale training and efficiency. Now, the second use case that we see an increasing amount of actually now, a lot of previous work has been very sort of large-scale training focused as more and more users are adopting ML models, especially open ML models. We're seeing an increasing usage of inference and this use case of building out an inference platform. Now, the concerns of an inference platform are a little bit different. Yes, we want to think about efficiency, but we need to think about efficiency in a slightly different context. And this context is really about optimization. This is a optimization problem. How do we ensure that we are providing the best throughput and the lowest latency for users, and of course at the lowest cost, unit cost? And the way that we do that is through a series of vertical optimizations that we provide in the platform, as well as horizontal optimization. So for vertical optimizations, we provide full level of control so users can tune their model, quantize their model, and sort of deliver the best performance of the model itself. We also have things like serving optimization through open frameworks that we adopt within the platform, things like VLLM and text generation inference. So we can actually leverage these sort of techniques in optimizing throughput through things like batching and other techniques. And ultimately, that's going to help us to minimize latency while increasing our throughput. And then the last is, of course, making sure that we have the right accelerator for the workload. And that's where having the most diverse set of shapes across GPUs and TPUs really plays to our advantage. Now that's vertical optimization. The other dimension is horizontal optimization. And this is actually where GKE shines. This is where we can do things like data preloading. So I can preload my model weights, and I can preload even things like my images for much faster startup and much faster scale up. I can do things like workload auto scaling. So I can now intelligently scale my workloads using a whole bunch of different metrics that we now expose through GKE. So users can have finest grain control over exactly how they want to scale and by which metrics they want to scale. And then we also have intelligent load balancing that's coming later on this year that allows users to now introduce their own custom metrics into exactly how they want to load balance across these serving stacks. Things like queue depth is a pretty common scenario for ensuring your load balancing across the right pool of resources for sort of optimum latency and throughput. And then the last is things like node auto scaling and auto provisioning. So we can now scale out our GPUs and our TPUs, and we can do that based on not only demand, but we can also do it based on the resource requirements of the workload, picking the right shape for the right workload based on its requirements. Again, another good example of customer that's doing this is Lightrix, and they're using, again, both TPUs and GPUs. And they're essentially using these to do sort of batch inference as well as online inference of diffusion models as well as their text models. And this is really giving them sort of the best performance across that set of accelerators. And then the last thing is the MLOps platform. And this is, again, where the open ecosystem is really critically important. And this, again, is where we're investing quite heavily. If you look at a really common scenario is leveraging something like Ray as the core job orchestrator that's under the hood. And Ray is extremely popular within the data science and machine learning community for a number of reasons, including its Pythonic API, as well as its highly scalable jobs API. But now if you sort of combine that with the scalability characteristics of GKE, you now have an amazing platform on which your data scientists can leverage these resources. And you can even deploy in a multi-tenant architecture for high utilization. So we'll talk about just a couple of core capabilities just to set us up, and then we'll jump right into the demo. So I'm not going to focus on all of these different capabilities. You've heard about GPUs and TPUs and how we can do some provisioning and placement. We talked a lot about scaling and ecosystem integrations, as well as batch job management and operations and governance. We're going to just focus on a couple here. One, I want to focus on scaling because it is critically important. And this will be very relevant to the demo we're going to pull up here momentarily. So if you think about the time to readiness, that's really the metric that we care about. What's the time from initially making a request saying, hey, I want this resource to be able to serve this model? What's the amount of time between that initial request and that server who has that model loaded into GPU memory, ready to serve the request? And there's quite a lot of steps along that journey. And really the idea here is we want to optimize that time, reduce the time from initial requests to serving as quickly as possible. And we do that in a few different ways. One, which we'll show you here momentarily in the demo, is what we call container preloading. And the team actually internally who leverages GKE as a core part of their foundational platform, we heard from earlier, Vertex AI. So Vertex AI is an internal GKE customer. And when they use this feature, they saw 29 times faster mounting for a 16 gig container. So that's significant improvements. We're talking about going from minutes down to single seconds. And those things really add up when you think about the level of scale for a lot of customer deployments. The second is data. So how do we ensure that data, specifically things like training weights or training data, are available to the container as quickly as possible? And one of the ways in which we expose this directly in GKE is through what's called GCS views. And GCS views is basically taking an object store in GCS and making it directly available to the container. So you can do quick pull, caching, read writes, etc. And then the last thing I'll highlight before we flip over to the demo here is in batch job management. And this is incredibly important, of course, with large-scale training runs, but also in multi-tenant deployments. And one of the sort of key aspects of any kind of batch scheduling system is how do you ensure that you have the resources needed to run the batch job when you need to run the batch job? So if I'm running a training run or I'm running some sort of fine-tuning or something like that, how do I ensure that I get the right resources, the H100s or A100s or any specialized resource that I need to run my training? And the way in which we expose this to customers is what we call dynamic workload scheduling, or DWS. And it comes in two modes of operation. One, it comes in flex start mode. So I can say, I need 20 GPUs or 20 instances with H GPUs each. I need it as quickly as they're available, and I need it for 7 days in order to do my training. And what we can do with DWS is I can put in that request and I can attach a job or a series of jobs to that so they can automatically execute as soon as those resources are available. And we've seen customers go from having a pretty difficult time getting GPUs down to getting GPUs in a matter of minutes in some cases. The other mode of operation is what we call calendar mode, where instead of saying I want them as soon as possible, you basically say I want them between this date and this date. And that is very common for a lot of training and fine-tuning scenarios. Okay, now onto the demo. Now, what we're going to show in the demo here is really an optimized inference demo. And we're going to show three things. First, we're going to show how to deploy or what a deployment of a text generation inference server looks like with Gemma 7B. Now, I'm just going to show you, I'll give a little spoiler here. I'm going to show you a video because really what I want to show you is how quickly we can go through this sequence. So we don't have to wait for containers to deploy for tens of seconds. I'm going to show you in a condensed video, but I can show you the live portion as well. So we're going to show an unoptimized text generation inference server with a Gemma 7B deployment. And by the way, that's roughly 10 gig container image. And for those of you who are very familiar with containers, a 10 gig container image is crazy, but that's where we're at right now. So we have a 10 gig container image, and we've got a 7B, about 17.2 gigs for the model weights themselves. Right. So very large amounts of data. We're going to do the initial deployment unoptimized. We're going to do the next deployment where we use persistent volume claims. So we're going to essentially pre-cache some of this data within a PVC, and we're going to share that across instances. That's going to give us some optimization. And then third, we're going to redeploy that with a preloaded image. And I'm going to show you how to get from hundreds of seconds to do this unoptimized deployment down to single-digit seconds. All right, so let's go ahead and show you what that looks like. Perfect. Okay. I promise I can show you this live as well. I'm just going to show you the recording because I'm going to skip through time here. We're going to use the power of editing magic so we don't have to sit here for about 10 minutes to run through the whole thing. We're going to do it just in a few minutes here, and I'm going to show you what this looks like. So what we've got set up here is an environment. This is connecting directly. Oops, sorry. Hopefully you can all see that okay. So this is connected directly into a Kubernetes cluster. And I just have a little visualization on the bottom here, which demonstrates the pods that I have up, the amount of time it takes to pull down an image, and the amount of time it takes to pull down the weights. Again, as a reminder, we're talking about tens of gigs of both the images and the weights, right? And what we're going to do is I'm going to show you a sequence of deployments. Again, the first deployment is going to be unoptimized, and I'm going to show you basically how long it takes, and then we're going to show those optimization techniques as we go. All right, so, and we've got our first setup. We've got a cluster with 2 GPUs, these are L4 GPUs, and we'll let this run. So we're basically doing an initial deployment. We've got this container running. Takes roughly 136 seconds or so to do the image pull. So not great. That is time that we're basically just waiting idle. That's a GPU that is idle, not being utilized. And then once that is pulled down, then we need to pull down the weights. And that takes an additional 113 seconds. So roughly 250 total seconds in order for that to be ready to serve. We can do better. So we're going to rerun this again. We're going to do a PVC in this case. So we're going to now share the weights across multiple instances. Since we're using an existing node, we get caching, which is great. So 0 seconds. Oh, sorry. I'm going to pause that. So 0 seconds for the first pull. That's great, right? But we do need to download the weights. And we're going to do this through a PVC, meaning that they're going to be pre-cached and they're available to multiple nodes. So we should get some pretty good optimization there. But you'll note we requested multiple pods. So we're going to try to scale this thing up, and I'm going to show you also what a cold start looks like here as well. So through the power of editing magic, we'll show you this will run roughly 54 seconds, which actually isn't bad considering we have our pre-cached image. But if we were to run this on the second node, well, then we've got to pull down the image again, and we've got to pull down the weights, which is going to take a little bit of time. So we'll run this one more time, and you'll see, roughly what 180-ish seconds or so for the second run. So, okay, significant improvement from previous, but we know we can do better. And one of the ways in which we're going to do better is we're going to pre-cache this image. So I'm going to pause here for a second. So what we've done now is we have another node pool. You can see them. I have node pool A, node pool B, node pool A and node pool B. What I've done is I've set up this node pool and I've actually used container image preloading. And container image preloading basically takes that image, I bake it as a disk, and I attach it to that node pool. So now anytime a new node stands up, it will automatically load this container image into the containerd cache. And that means that when containerd starts, it's always going to look into cache first. It's going to try to pull those images up to stand up the container, and it's going to move pretty quickly. So now we can take what was 180 seconds or so, if I remember correctly. I don't even remember my own demo time, but something like that. And we're going to get it down to 4 seconds. So that was a clean deployment, nothing deployed on it yet. We stood it up, and we now have that very large image in 4 seconds. And because we're now using PVC to share those weights, we can now get that down to roughly, what I think it was about 60 seconds or 50 something seconds or so. So we've now taken a process that was, in the 200, almost 300 seconds to run end to end, and that's 300 seconds of wasted time, down to something that is much, much more manageable for a scale out scenario, which is, roughly 60 seconds or so. Sorry, I'm just getting through this last part. So we were able to get this ultimately down, I think yep, there we go. 64 seconds. So that was sort of our final optimized state. And we can keep optimizing this even further. We can now start to even bake in our weights directly into our container image. So I can get this down ultimately to single-digit seconds for both the container image as well as the weights through some of these optimization techniques. And these are available just directly through GKE as core optimization features, and something that our customers who are doing both optimization for training, but also for, especially for inference, are super excited about. So I will pause there, see if there's any questions about the demo. Otherwise, I can show you what it looks like live. Otherwise, we'll pause for questions.
So when you do the preloading, there's still an amount of time to bring in the container into. I'm just trying to understand where the preloading actually occurred. It didn't occur during the seconds that you're clicking off here, but somewhere it occurred, right?
It did. So we're basically moving from a runtime operation to a build time operation. So you're absolutely right. Here, let me show you what that looks like. So yes, we are taking what is a runtime operation where we're lazy loading essentially those container images when they're needed into the cluster to a sort of a build time operation. And that's something we would automate. Every time we want to have a new container image, in addition to building our container image, we can basically mount that directly to our node pool. So we showed like the deployment here. I promise this is real. This is running live here. So in order to actually do the preloading here, what we're going to do is run a CLI to actually generate the image. So I'm going to pass in this text generation inference image, which is my container image. And all I'm going to do is basically then build an image that I can attach to a cluster. So that's a simple one-line command. And then when I create a node pool, I have the ability to now pass in that image. You can see the image name right here. So it's a bit of a different model than we've been sort of used to in the Kubernetes and container ecosystem for the last decade, where instead of always just pushing container images to an image registry and letting the runtime pull them down, we're adding this additional step, this optimization technique, where we can now start to mount them directly to the node pool. So an additional consideration for operators, but considering these are container images that have optimized layers, we can provide sort of base images, and that even just with CUDA kernels being significant as they are, there's lots and lots of optimizations we can do even just by using a base image and preloading it with this technique. Just wrap it up here, and then yeah, lots and lots of resources out there. Encourage you to check them out. We provide tutorials and guides and reference architectures and things like that for customers that are looking to build out platforms on GKE. So recommend you check those out. But otherwise, I will hand it off to the next presenter. Thank you so much.